Hi, in this video, we want to take a look at correlation coefficients. So the reason why we're going to be doing this is because upcoming videos are going to be looking at factor analysis, and we're going to need to understand correlation pretty well before we can really dig into that and understand what's going on. All right, so Pearson correlation is the by far most familiar, most understood version of correlation. Actually, let me back up. Correlation is, I'm going to use this colloquially for the moment. Correlation is looking at the correspondence, the relationship between two variables. Okay, so if I have numeric data, the standard classic way to measure correlation or correspondence between two variables is to use Pearson correlation. This is the projection correlation, and this corresponds to like the linear algebra sense. Now, the next most common one to be looking at will be for Spearman correlation. And here, what this does, this takes the data and it takes the rank of the values and then does correlation on the rank, Pearson correlation on the rank of the values. That's not 100% correct because of ties, but that's close enough for thinking about it. So that type of correlation can handle numeric data and it can handle ordinal. So it handles, let's see, ratio, interval, and ordinal. Okay, Pearson only handles numeric if we're doing it correctly, because yeah. Now, what about when we have something a little bit more exotic? What if we have something that's, let's say, binary? Well, binary, we also have Kendall's tau, which looks at the concordance between variables. That works very nicely. My personal experience is that takes a while to compute at times, but it's still informative. Now, the ones that we want to look at here are a little bit more exotic. And so we're interested in the situation where we have nominal data, binary, dichotomous data, or we have ordinal data. And so here, what we're going to be doing, we're going to be trying to get a correspondence between two variables where we're going to be using a method that doesn't work unless it's, that doesn't work for the classical situation of correlation. All right, so two options for evaluating the correspondence between variables that are dichotomous or ordinal is Tetrachoric and Polychoric correlations. All right, so these correlations assume that the data are actually the output from a multivariate normal distribution. Okay, so this is kind of a big concept with this, is that under the hood, something that I can't actually see is that there is a multivariate data or multivariate population, I say population, that is kind of driving what I actually see. So for example, if we were to model like academic proficiency, with multivariate normal, and then I give a test, well, one particular question would correspond to some like a dimension on that multivariate normal. Well, if I give them a test, I see zeros and ones. I don't actually see the true the population that I want to see. I see the output from something else that's driven by the population that I'm interested in. All right, so the observed values correspond to a marginal normal distribution. So marginal normal. So here I have multivariate normal, but if I look at one dimension at a time, I see a bell curve. Now, what we're going to do, since we don't actually see what's going on, truly what we want to, like what we would really want to know for this problem is the multivariate normal. We would like to know that, but we don't. Remember, if I'm using data, I don't know what's going on. So what we're going to do, we're going to go ahead and say, hey, marginally, it's going to look like standard normal because I have no other way of estimating all these parameters. And so what we're going to do, we're going to say, all right, when I look at one binary column, I've got zeros and ones. If it's above a certain criteria, it's a 1. If it's below a certain criteria, that same criteria, it's a 0. Okay, so there's a threshold here. And that is our model for how we observe the data, what comes at us. All right, so what we're going to end up doing, if I want to go one step deeper, I can use bivariate normal on a 2x2 contingency table to get even more information about what's going on. So I'm going to use the 2x2 contingency table to get an idea of the correlation between the different dimensions of the multivariate normal. All right, so this is kind of a slick way to go. Now, something to think about this is that if the under the hood population is not normally distributed, this is a really bad way to go. Now, if it was, t-distributed, Cauchy distributed, something that's bell curve, this will probably work out all right. But if it's something that's just completely, if the under the hood population is not normally distributed, this is a bad idea to be working with. So we have to have some subject matter knowledge to give us faith in this model structure to use. If I don't believe that this is the correct model structure, and when I say it doesn't have to be exactly correct, but if it's like grossly different, then I know I should not proceed in this manner. All right, so here for this example, we're going to use youth depression data from the Modern Psychometrics with R textbook. Oh, and here, this example is taken from Modern Psychometrics with R by Mayer, and there is the GitHub website if you want to get this code. I've modified it. I've expanded upon things, shrunk some things down, just so that it's more of how it emphasizes more of what I think is most important. All right, so we have this data, and if I look at this, I'll notice that for the CDI columns, these are the ones that are part of the youth depression index, is that they have 0, 1, or 2 in there. And it doesn't explicitly state it in the textbook, but it's implied that 0 is less than 1, 2 is greater than 1. Okay, so it's ordinal. Well, for the first example, we're going to use the Tetrachoric correlation, which only takes 2 levels. So I'm going to go ahead and convert this to zeros and ones. So 1 means it's 1 or 2 as I perform this analysis. All right, so to get things to go in the system, I go ahead and I convert it to an integer. And then anything that's greater than 1, so if it's a 2, I convert it to a 1. Now let's go ahead and look at the individual tables of each of these to see just how many we have. Now realize a 1 represents a 1 or a 2 from the original data. So I know that in the original data, it was less than or equal to 261 for the number of ones. So, and it was like 27-ish CDI columns. And then we have race is included in the data set, but we're not going to use race in this example. All right, so here, let's do tetrachoric correlation. Okay, so what we're going to do, we're going to take like 2x2 tables, and we're going to assume that each column of zeros and ones is the output from a normal distribution, a standard normal distribution. And we're going to say, hey, there's some threshold, some criteria on that normal distribution. If it's above the criteria, it's going to give me a 1. If it's below that criteria, it gives me a 0. Okay. Then what we're going to do, we're going to go pairwise. And we're going to look at what do I get for the 2x2 contingency table. And I'm going to look to see, what bivariate Gaussian distribution fits the distributions that I get and the data that I get as well as possible. All right, so we're going to assume marginally it's standard normal. So for each of the 2 dimensions under consideration, we have mean 0, standard deviation 1. Okay, so if you think about the bivariate normal, the only thing that's left as a parameter is going to be the correlation between the 2 distributions. All right, so what it's going to do, it's going to take the data and it's going to find the correlation that best fits the observed 2x2 contingency table. And so when I do that, I can see these values. So like the bivariate normal distribution that's fitted to the first and second CDIs has a correlation of 0.5 as a parameter. the bivariate normal correlation between CDI1 and CDI3 has a rho of 0.54. And we can go down the list and we can see all the pairs. So there's a lot of them here. So in this multivariate normal assumption, we are actually really just assuming that pairwise we have bivariate normal. It's a little bit weaker than multivariate normal, but it's just a lot easier to articulate, a lot easier to think about if we just assume it's multivariate normal. And we can see that there's a whole bunch of them. Now here, these are the individual cutoffs for each of the individual distributions that leads to the zeros and ones in the columns. All right, so if I see 1.16, I know that's to the right of one standard deviation to the right. Okay, so that gives me an idea of like how extreme it is. So if it's a negative number, I know that it's going to be less than the mean. If it's a positive number, it's going to be greater than the mean, right? Well, how they actually construct this is that the cutoff is always greater than 0, by the way. But if I look through here, I can see that 0.3 means that there really isn't, the threshold is very close to 0 on that bell curve. If I look and I see, let's see, what's a big one? 1.3, I'm looking through real quick. Yep, so 1.3, that's the one that's the farthest to the right of our group. All right, so that's going to be the most extreme threshold of all of them. Okay, so let's go ahead and look at individually. Let's look at 2 of them. So what I did, I went through and I looked at the correlation between all of them, and I found the 2 that had the greatest correlation. So if I look, so 1 and 10. If I look here, I can see that we have a rho of about 0.8, and that's going to be the largest one on the entire table. All right, so I want to show you what the bivariate normal distribution looks like. All right, so down here, all right, there we go. Down here is CDI1 along this axis. So this is this corresponds to the normal distribution corresponding to CDI1. Now, this is going to be the modeled cutoff for CDI1's normal distribution. So if the modeled normal distribution is above this point, the observed data gives me a 1. If it's below this point, the observed data gives me a 0. If I look here, this axis corresponds to CDI10R. If I see a value, or if the modeled normal distribution for CDI10R is greater than this point, we have a 1 in our data. If it's below this cut point, then we have a 0 in our data. Okay. And then we have over here, this corresponds to all the observations that are both 1 in both of the 2 observations. Here, both the observations are both 0. And in this corner here, we have a 0 for CDI1, a 1 for CDI10R. Down here, we have a 1 for CDI1 and a 0 for CDI10R. Okay, so now what is this ellipse? This is a contour plot. So I believe that this will be probably like a 95% contour plot. So this is modeling, if I was to plot all the dots, approximately speaking, the data that led to, or sorry, the population data that I did not see that led to the data that I saw, we believe that 95%, under this model, 95% of the unobserved data would fall inside this bigger ellipse. And probably about 60, I think it's going to be 68% will be in this ellipse. I couldn't find in the help documentation how big the percentage ellipses were, but 68 is pretty common, 95 is pretty common. You know, it corresponds to, you know, standard normal aspect. And that looks about right when I eyeball it going over this way and going up this way, like that. Okay. And so there's a contour plot. Now, if rho is big and positive, then it's going to be very, very narrow. If it's big and it'll be going in like a positive slope direction. So here, the wider this part is, the smaller rho is. The smaller this is, the bigger rho is. Okay? And if it was a negative correlation, the ellipse would be pointed this way. So this gives me an idea of what's going on. And for each of the pairs of binary data that I have, I can make one of these plots to guide me on what's going on, what is the relationship. And so if I see that this is a very narrow ellipse, it's almost a straight line, then that indicates that there is a stronger correlation. Now, polychoric correlation is very similar, but it works off of contingency tables that are larger than 2 by 2. It could be 3 by 2, 2 by 3, could be 10 by 9, could be any integer values where one of them is greater than 2. Actually, it could be a 2 by 2 also. All right, so everything looks very much the same. Here I'm reloading the data because in the previous example, I overwrote so that we had 1s instead of 2s. And now I'm just going to go ahead and run it with the raw data because this will accept factor data. It needs to be ordinal for this to make sense, by the way. Otherwise, the whole normal aspect doesn't really work out. And here we have the multivariate normal correlation estimates. Now, when I look at the cutoffs are a little bit more complicated. So in the tetrachoric correlation, there was just one cutoff for each individual variable. Well, now I've got 2. All right, so this one is the cutoff between 0 and 1. This is the cutoff between 1 and 2. So greater than this value, it's a 2. Greater than this value, it's a 1 or a 2. Less than this value, it's a 0. And then we just go down the list like that. So this gives me an idea of what's going on nicely. So once again, I can go through and I can draw the ellipses plot. And when I do this, what I'm doing is I'm just grabbing the row once again, and I'm grabbing the cutoffs and doing exactly the same thing. But the difference here is that there's actually, this should be a 3 by 3 grid both times. I couldn't get R to slap on another line. I wanted to keep things parallel. But here is the cutoff between 0 and 1. Here's the other cutoff between 0 and 1. And up here, there would be another cutoff. So if I look up here, it would be, oh, I can't tell because it doesn't label it. 10, I think, is the 9th one. I think these are the cutoffs I want. So 2. All right, so there would be another line here, and then another line here. And you would see I would actually have a 3 by 3 grid showing the values I would get. And we can see, like, visually where most of the data is landing. And of course, it's going to be in the 0, 0 corner. And we would have a relatively narrow strip here if I could add on those lines. Unfortunately, I can't. And we can see, like, observing a 1, 1 would be pretty rare, actually, in this data set. But a 2, 2 would probably be more common. And we can get an idea of the magnitude of how frequent things are just off of this visualization. All right, so now something about this. If I'm using discrete data, and I'm using that discrete data to get continuous distributions. So anytime you do something like this, it comes at a cost. All right, so the output is not always stable. When I say stable, that means if I was to change a few values, I can get very different outputs. All right, so stable means if I was to change something a little bit, I could get a big difference in output. All right, so when I have like paired levels, only have a few observations. So like 1 and 2, 0 and 2, 2 and 1. If paired levels only have a few observations, then a few observations in there or a loss of a few can change the output by quite a bit. Now, if paired levels have 0 observations and correction is true, so the correct parameter is saying, hey, make an adjustment to make sure I don't, make sure things computationally work out better. Well, what's going to do is going to put 1/2 into the computations. Well, what'll happen is if I have a lot of these corrections, I can get unstable results. Now, another thing to think about is if I was to actually go through and compute all of these, because I'm working bivariate and I'm not working multi-normal, since I'm only using 2 at a time instead of what would theoretically be multivariate normal, it can work out that I get basically gibberish output. Now, what do I mean by gibberish output? If I have true correct correlation matrix for a multivariate population, then I've got certain properties on the correlation matrix that will automatically happen. If you take a regression theory course with me, I will spend a lot of time on this concept. Here, we don't need to worry about it. Basically, the punchline is if I see negative values in my eigenvalues, I know I have a problem. Okay, so if I have a good correlation matrix, then all of the eigenvalues are going to be 0 or positive. More than likely, they're going to all be positive, but 0 is a possibility. So if I see any negative values in my eigenvalues, so what's going to happen? I get my correlation matrix. I take a look at the eigenvalues. If I see negative values, then was like, whoa, 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 something's wrong. I know that things aren't supposed to be this way. So what do I do? Well, if I didn't smooth, I'm going to smooth. If I did smooth, I'm going to not smooth. I'm going to see which one gives me the better output. All right, so let's say that I take the R motivation data set from the same package. And here I'm just grabbing the binary data using some string logic, a grepl. And then I'm going to go through and I'm going to run the tetrachoric correlation, but I'm not going to do any smoothing. All right, so I'm going to run the correlation and it's going to go 2 variables at a time and it's going to compute that row, assuming that we have bivariate normal. Okay, well, when I'm all done doing that, I take the eigenvalues. I know that if I have a good modeling correlation matrix, if everything went the way it's supposed to, I will not have any negative eigenvalues. I look here, boom, I've got 4 of them. Okay, so now I need to make a decision. Is the magnitude and frequency of negative enough that I don't worry about it, or do I change things up? Need to make a decision. All right, so what the author chose to do in this example, he was like, you know what? I don't like this. So what I'm going to do, I'm going to change this parameter smooth to true and see if that improves the situation. So it's going to technically be a different model. And here's a warning that comes out, is that the matrix was not positive definite. Smoothing was done. All right, so positive definite. So the machine is going, hey, 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 this is not behaving like a correlation matrix, you know, like it's supposed to, because if it was truly, if the data was 100% consistent with a multivariate normal, there wouldn't be an issue. But in real life, data is ugly. Data doesn't fit the model that we have, that we want to use, or the model we have to use. And so we're running it and we go, hey, it doesn't perfectly match. Now, it doesn't mean throw it out. It means, you know, double check, make sure it's the right thing to do. All right, so I go through and I run smoothing. I check my eigenvalues. And now here I can see that we have, you know, the 0.08, 0.05. Now here, all of these are 0. It's so, I mean, it's not exactly zero in the machine, but I might as well call them zero. All right, so these 4 values, when we did the smoothing, got converted over to 0. Now, I have to ask myself, is 0 good enough? Now, up to rounding, you know, the machine is saying it's not exactly 0, but looking at that, yeah, that's, you know, for all practical purposes, that's 0. All right, so I do not have a positive definite matrix. I have a positive semi-definite matrix. And theoretically, I would like a positive definite, but I would go ahead and proceed with this as is. All right, so the punchline of this part is after I get my correlation matrix, I want to check and see, do I have any negative eigenvalues? If I don't, I want to switch my smoothing parameter to see if I can improve it. Well, that's all I've got for you. Take care and goodbye.